We pick up from part 1 of module 3.7 by applying some of the concepts we've learned thus far to estimating the probability that a call option is in the money. Now, it turns out if we assume the terminal stop price is log normally distributed, then we can represent the random stock price, terminal stock price, is simply equal to the current stock price e to the mu. We need to subtract off the sigma squared over 2 because of the feature of the asymmetry within the log normal distribution. And these are annualized numbers, so we need to multiply by time. Remember, annualized volatility is linear in the square root of time, and then we multiply times the epsilon, which is a standard normal, mean 0, standard deviation 1, a random variable that we covered in a previous module. So we could actually simulate this and then just count the number of times it's in the money divided by the total number of observations, and we'll get an estimate of the probability of being in the money. There's a much more efficient way of doing this. We can basically analytically solve for the probability that the stock price is above the strike price. That is the probability that this representation of the terminal stock price is greater than the strike price. With a little bit of math and rearranging, we basically can conclude that the probability of a call option being in the money is the familiar ND2 variable out of the Black-Scholes-Merton model, with the exception that it has our subjective estimate of the mean in it. And so one direct application of the analysis and analytic tools that we've developed thus far is to be able to estimate things like the likelihood of being above the strike price. Obviously, we could then compute the likelihood of being below it. We can compute likelihoods of being in different regions. You could think of multiple strike prices. There's a whole host of things we can now do in our analytic work. We turn now to multivariate distributions. Finance suffers from what's known as the curse of dimensionality. If you're coming out of the natural sciences, you're familiar with working with 3, maybe 4 dimensions, if you three-dimensional space and time. Or if you subscribe to string theory, there might be 10 or 11 different dimensions. And so in physics and math, typically the dimensionality is somewhat limited. But if you think about the S&P 500 index, it's technically a 500-dimensional problem if you model each stock as a different dimension. Unfortunately, each stock has multiple factors or dimensions, and so you quickly get into this curse of dimensionality. And thus, as a quant, you want to aggressively seek to reduce the level of dimensionality. In practice, however, one rarely gets the dimensions down to only 1. Like the capital asset pricing model, where you only have one variable, the beta, it's just very rare that actually works in practice. Hence, we need the capacity to model multiple dimensional problems. When we get to dynamic risk measures near the end of the book, we will turn to multivariate random number generation. But at the moment, we'll just focus on the bivariate. But in general, the multivariate normal distribution can be represented in matrix form this way. It turns out we could compute a variety of different statistics coming out of that analytic PDF. With the bivariate PDF and CDF, we can represent the probability density function in this fashion. If I integrate over the 2 dimensions, x1 and x2, then I can compute the CDF. The log normal distribution is just slightly more complicated. Notice that you have the x1 and x2 variables in the denominator. Hence, the log normal distribution assumes that the x1 and x2 cannot be 0. If we do a simulation, a bivariate log normal simulation, we get a distribution that looks something like this, and where the outcomes are concentrated near 0, but then they spread out on both the x and y axes. Conditional normal distribution, there are times, particularly in risk management, where we want to take the conditional expectation or some calculation of that nature. So at the end of Module 7, we cover some of the technical details of the conditional normal distribution. And so the next several, to conclude this presentation, we're just going to look at several graphs generated in R, and then we'll turn to quickly go over some of the R code. And so this is the univariate normal distribution. Notice if the volatility is 30, you get a symmetric distribution of this nature. If I raise it up to 80, it looks like this, 130, and then 180 standard deviation. Basically, the PDF just flattens out. And if we're modeling stock prices, one complaint about the normal distribution is that it admits the possibility of negative numbers. One way to easily handle this problem is limited liability for a corporation is basically a zero-strike put. Limited liability requires incorporation, so it's not a technically free option, but you could easily model stock prices with a log normal distribution overlaid with a limited liability put. The log normal distribution PDFs with comparable standard deviations calibrated to the normal distribution, what you quickly notice is the log normal distribution collapses, that the mode collapses towards zero, and you get a very unusual distribution that leaves me uncomfortable with the log normal distribution, particularly with extremely risky financial instruments. The normal CDFs are fairly well behaved. The log normal CDFs have some peculiar behaviors, especially for high standard deviations. We could simulate, just by way of reminder, the mean, median, and mode. The mean remains constant. The median and mode decline. The probability of being in the money as I raise volatility actually changes, and I'm not sure that makes intuitive sense that as I raise volatility, the probability that the put is in the money goes up. Whereas if I raise volatility, both the median and mode declines. And so we could run samples. We could get a log normal distribution easily, either directly or indirectly. The bivariate normal can be found by just doing a double integral or a host of other different methods. This is one quadrant of a bivariate normal CDF based on, actually it's the entire range based on the double integral. And we see that the symmetry that's there with the CDF. So in summary, we've explored the log normal distribution and the normal distribution. We looked at some of the technical properties, and we'll now turn to examine briefly some of the R code. We now quickly turn to examining some of the R code provided with Module 3.7. If you just double click again on the RPROJ file to load this particular set of R code. Again, if I just take this out, if we look at the files, let's first take a look at the integration test and get rid of these results. Remember, if we clean out wherever things were left off in the past, just run those few lines of code. Stats is the only package that I'm using. If I assume a stock price of 100, strike price of 100, interest rate of 12%, which is essentially my mean, dividend yield of 0, volatility and time to maturity. Now, what you'll notice in this particular set of R code is that there is a large number of normally distributed functions provided, as well as log normally distributed functions. So if I run that one line of code, what you'll notice is there's a huge number of functions that are now available to me, If I run the lognormal distribution code, I have even more variables available, or functions available to me. And so I would encourage you to get familiar with the different functions. Many of them don't do anything. For example, the normal skewness we know is 0, but just in case a user, when you write prototype our code, often users don't fully understand what they're doing. And so you want to provide them the answer even to questions that they shouldn't be asking. And so you'll find these built-in functions. And so these functions are very helpful. There's a variety of different ways to estimate the CDF. I could integrate as one way to do it. I could approximate it using an approximation method. And so I'm not going to take the time to go into all the different details. Basically, what I do when I build these kind of functions in our library of functions, I'll go and I'll test them and just see if, in fact, these numbers are correct. And I would encourage you to do the same thing. The integration methods, I can test the CDF of the standard normal, assuming d equals 0, should be a half. And so there's a variety of ways to test these sorts of things. If I could estimate ND2 based on the parameters given above, in this case, the probability of being in the money would be 59.87%. And I could do a variety of other calculations depending on what my interests are. And so what this particular program does is it generates a variety of different outcomes that we looked at before. These are all the PDFs and CDFs that we did in the past. And then they're illustrated with different volatilities and plotted out. And so, again, you can just highlight this whole piece of code, run it, and examine what it does, and then explore how it does it. The other test program provided here is the double integral or the bivariate distribution. And so generally, I know this is going to generate a plot. And so if I make that a little bit larger and run this program, it takes a little while to run. At the end of this package, just for fun, I found some stuff on the internet to generate some cool looking graphs that you can then modify. This is volcanoes, I think, in Australia. This is just an interesting mathematical function and different properties of it. This is the more interesting finance application, is a bivariate normal PDF, depending on the area that we're examining. If you introduce correlations, you can change the shape of this particular distribution. And so there's multiple ways to do the bivariate normal, and we can test for different errors of the different methods and come to some conclusions on which one we like. Bottom line is all the methods are extremely accurate and useful. And so I would encourage you, as you begin to learn this material, that you do spend time with the R code. Again, my recommendation is an hour a day, 3 or 4 days a week is probably enough at this point.